So last week you were doing an experiment to measure the length of time it took for a pendulum to complete one vibration, and you compared different lengths of pendulums, and what you saw was that the longer the pendulum, the longer it took for one vibration. So this means that long pendulums will take a long time to vibrate, whereas very short pendulums will vibrate very, very quickly. This is the principle used behind like a clock, like a grandfather clock, where you've got a pendulum, and by setting the length of the pendulum to just the right size, you can make sure that it takes exactly 1 second for each vibration. Other things like this are like a metronome that a musician might use. They have sort of an upside down pendulum that will vibrate from side to side like that, and by changing the position of a weight, it can vibrate faster or slower so they can keep in time with the music. With vibrations, however, we often don't measure them by the length of time for one vibration. What we do is we refer to something called the frequency, and that's how many vibrations there are in 1 second. What you measured last week was the length of time for one vibration, and that is known as the time period, or sometimes the periodic time, or sometimes just the period of a vibration. So that's the length of time it takes for one vibration. As I said, we often refer to something called the frequency. It's similar to the word frequent, and that's how many vibrations there are in 1 second. Now, it's very simple to work out what the frequency of something is if you know the time period. The unit of frequency that we're going to use is called the hertz, which we shorten to a capital H and a small z. Maybe you've heard the word hertz before, or megahertz or gigahertz. So 1 hertz means 1 vibration per second. 10 hertz means you get 10 vibrations per second. And if you get a frequency of less than 1, like 0.5, that means you get half a vibration per second. The way we work out a frequency is we get our time period and we divide 1 by the time period. So we have a formula to use. Frequency equals 1 divided by the time period. I use the letter T for time period, a capital T. Small t normally just means any amount of time in physics. We're going to use a capital T. So frequency equals 1 over t, and that's a formula that you're going to need to learn. That can be rearranged to say that the time period equals 1 over the frequency. So if we know the frequency, we can work out the time period. And if we know the time period, we can work out the frequency. So let's say here's a simple example. If a pendulum has a time period of 2 seconds, t equals 2. In other words, it takes 2 seconds for one vibration. We can't get one vibration fitted into 1 second. In fact, we can only get half a vibration fitted into 1 second. We need 2 seconds for a full vibration. So we write down our formula, frequency equals 1 over t. We put in our number, so t was equal to 2. There's our answer, 1 divided by 2 is 0.5, and our unit is hertz. Let's think of another example. Let's say something had a time period of 10 seconds. In other words, t equals 10. So the frequency equals 1 divided by t equals 1 over 10 equals 0.1 hertz. Let's say something had a time period of less than 1 second. Let's say something had a much faster vibration. It only took 0.05 seconds for one vibration. So our frequency equals 1 divided by 0.05, which is equal to 20 hertz. So if you've got a frequency that's bigger than 1, it means you've got a vibration that takes less than 1 second. And the bigger the frequency, the higher the frequency, the less time it takes for one vibration. In other words, the faster something's vibrating. In the future, we're going to have a look at how the frequency of a vibration affects sound. So far, this topic is about sound, but we haven't really talked about sound yet. So we're going to start to look at vibrations causing sound, and then we'll have a look at how changing the frequency changes the sound. Last week, we introduced the idea of sound and vibrations, but we haven't really talked about how they're connected. But what we did see is I showed a rubber band being twanged and a ruler being sort of sprung over the end of a table. And what we see that for a sound to be produced, something needs to vibrate. That can be something like in a drum. When you hit a drum, the skin vibrates, or you pluck the string in a guitar, the string vibrates. Whenever you speak, air passes over your vocal cords, sort of tightly strung cords in your throat, that make them vibrate to give us the sound of our voice. Everybody's vibrates in slightly different ways, which is why we all have slightly different voices. Now, you maybe haven't come across atoms and molecules yet in chemistry, but you will eventually. Everything in the world around us is made of tiny, tiny, tiny little bits, particles. They're known as atoms and molecules. We're not going to worry too much about what they are at the moment, but you just have to remember that everything is made up of little tightly packed atoms and molecules. Different things have different particles. Sometimes the particles are very close together, like in solids or liquids. Sometimes the particles are more spread apart, like in gas. Sometimes the particles can sort of stay locked in one position, like a solid. Other times they can flow past one another, like in a liquid, or sometimes they fly around at high speeds and bounce around everywhere. That's like a gas, like the air. You'll come across that at a later stage in chemistry. But they are what's needed to carry sound. So when a sound is produced, the atoms and molecules, the tiny particles make up everything in the air, carry the sound from one place to another by vibrating. And I'll show you a little animation now of what that looks like. Here we can see a bit of a demonstration of the particles in air vibrating to carry sound. So here we've got a pile of blue dots, and those dots are going to represent the particles in air. Now, that's not a real life example because in air the particles are moving around at random, up and down, left, right, forward, backwards, bumping into things, moving around. But we'll not worry about that here. Whenever we play a note on our keyboard, you'll see something interesting. You'll see these ripples occurring. And I'll do that again. Hopefully you can see sort of dark bars of the dots moving up the screen. Almost if you blur your eyes, it's easier to see the bars moving up. And those dark bars are made by the particles squashing together, getting closer together. And in between the dark bars are lighter bands caused by the particles spreading apart. Now, what's interesting is if you look at one particular dot and focus on that one dot, not anything else, just that one dot, let's see what happens. Well, the dot doesn't go anywhere. It moves up, but it moves back down, and up and down, and up and down. It vibrates. The dark bars travel up the screen and keep on going up the screen in a way. But the particles themselves just vibrate. Dark bars are representing sound waves. They're what we call compressions. Little bits of higher pressure. And they will push the sound along towards our ears. So we hear something when those compressions and reach our ears. The white bars in between them, where the particles spread apart, are called rarefactions. You don't need to worry about those terms. But they're basically changes in air pressure that what we detect as sound. If I produce different notes, you should see that the particles vibrate at different speeds. So low note has a slow vibration. A high note has a much faster vibration. Don't forget, we've just looked at frequency. So slow vibrations are low frequency. Fast vibrations are high frequency. This is what's known as producing a sound wave. You can have a look at this yourself if you go on the internet and search for, as you can see at the top of the page, Chrome experiments. And you can go to the music lab and you can play around with things like this yourself. Let's get back to your notes. So we saw that sometimes those particles squeeze together. They come together, they form a little high pressure bit. That's called a compression. And sometimes the particles spread apart. They have a lower pressure, and that is called a rarefaction. You don't really need to worry about those two words for this topic. So those moving molecules, they really carry sound energy from one place to another. And you need these particles and their movement to carry the energy. So if you hit the drum, the particles squash and stretch and squash and stretch. And here we'll have a little look at a video at something vibrating to produce sound. We'll also then see some evidence of the air, the particles in the air, moving and vibrating to carry this energy. We'll see that in a candle flame. What do we need to produce sound? Well, as we already know, we need a vibration. And the vibrations that produce sounds that we can hear are usually fairly fast. What I've got here is a loudspeaker, which through an amplifier is connected to an iPad. And so by playing the iPad, we can make some sounds. What I want you to do is have a look at this cone. This is the part of the loudspeaker that vibrates. If I produce a high-pitched sound, we can't see much happening. If I produce a much lower note, hopefully you can see that the cone is moving quite noticeably. It's vibrating and producing the sound. Now, normally we don't see this because most of the sounds that we hear, the vibrations are really a bit too fast for us to see. But this is vibrating slowly enough for us to see. In fact, let's see what it looks like in slow motion. And vibrations are how the sound travels from the source, in this case the loudspeaker cone, to our ears. The vibrations pass through the air. The particles that make up the air, well, they vibrate and then pass that vibration on to neighbouring particles and neighbouring particles right the way through till they reach our ear. We can't see this happen because we can't see air. So what I've got here is a candle, and if I light the candle, the flame of the candle is in the air. If the air vibrates, then the candle flame should also vibrate. Again, we can't see it with the high-pitched sounds, but with the low-pitched sounds, where the vibrations are slow enough for us to hear, I'll bring it in nice and close. Hopefully you should see that the flame is vibrating at about the same speed as the cone. And that's because the vibrations in the air are the same speed as those produced by the cone. Now, sound can travel through all sorts of things. It can travel through air, obviously, but I'm sure if you've been under the water in a swimming pool, you've heard of sound there before. Or if you put your head down on your desk and tap your desk, it should sound louder, especially if your ear is pushed down to the desk. So sound can travel through the solid of your desk, or it can travel through the liquid of a swimming pool, or the gas of an air. And in fact, the particles, as long as there are particles, the closer those particles are packed together, the faster sound is going to be able to travel through things. So the closer the molecules are, the faster sound will travel. Basically, the particles, when they move and vibrate and sort of pass those vibrations on to the neighbouring molecules or atoms, they can do it more efficiently when they're closer together. So the molecules don't have to move very far to hit one another. So sound energy will be transmitted more rapidly in water than the air, because the molecules in water are much closer together than they are in air. Sound is very fast. The speed of sound in air is about 330 metres per second. 330 metres per second. In other words, it goes 330 metres every second. It's not exactly that. It can be a bit faster, a bit slower. It depends on the temperature and humidity and air pressure and all sorts of things like that. But that's roughly the speed, which is very fast, about 740 miles an hour. But it's not instant. I'm sure you've maybe seen things that are loud but at a distance. So maybe at a sports day you've seen somebody with a starter pistol and they've fired a gun and you're at the other end of the track and you can see a little puff of smoke and a fraction of a second later you hear the bang. Or maybe you've been to the air show and you've watched some of the fast jets flying along and the sound looks like it's coming from behind the jets. It takes sound a bit of time to travel to you. Not a huge amount of time, but you can notice it if it arrives half a second later than you expect. That difference in what you see and what you hear is because light is so much faster than sound. Light travels at 300 million meters per second. So it's about 1 million times faster. So it's instant. As soon as the starter pistol fires, you see the puff of smoke. As soon as the plane flies past, you instantly see where it was. It's not quite instant, but it's just so quick that you can't tell. The biggest example of this is thunder and lightning. Thunder and lightning are produced at the same time. The air explodes, gives it a flash of light and a burst of sound. But you see the lightning before you hear the thunder. The light travels to your eyes pretty much instantly. But sound can take much longer to travel, especially if it's a distance away. 330 metres is very roughly a fifth of a mile. So if lightning were to go off about a mile away from you, the light would reach you almost instantly, but the sound would take about 5 seconds to reach you. So sound takes longer to travel, therefore you see the lightning before you hear the thunder.